this session, we're going to work on perhaps one of the most fundamental concepts of all of chemistry, the covalent bond. And we're going to deal with the simplest of molecules, hydrogen, the most prevalent molecule in the universe. Hydrogen gas. First of all, we know it's diatomic. That means it has two atoms. Always is diatomic. We know that if it is a solid, there's so little intermolecular attractions because it's a totally nonpolar molecule. Electronegativities of the two atoms are the same. That hydrogen is a solid. To get to a solid state, the intermolecular attractions, called the London dispersion forces, would take effect at only minus 259 degrees Celsius. That's cold. Probably need a sweater. So hydrogen is diatomic. We know that the hydrogen is indeed bound by a shared pair of electrons, and a covalent bond is a shared pair of electrons. We could draw it as that line, or we could use Lewis dots, put one hydrogen for the one and a dot for the other hydrogen, and say that this sharing of a pair of electrons between the two atoms gives each hydrogen at any one time equivalent to 2 electrons, which is a noble gas configuration. And we know this is one of the main reasons we get stability in molecules with noble gas configurations. So let's start. There are two things that we are going to know about every bond, and that is, number one, we are going to know that every bond has a specific length. And the second thing, every bond has a specific energy associated with it. Now that means to break the bond will take a certain amount of energy, and that same amount of energy will be involved in forming the bond. So let's start off with discussing the bond length of hydrogen. And I think what we'll do is use our tool here to draw an energy diagram. And on this axis we'll have potential energy here. Oops, let's get this out of there. Potential energy here. And I'm not going to talk about this right now. But this is the distance we're going to talk about. R is the distance. So between the atoms, the bond length. So we start with two atoms with a great distance between them. And as they get closer and closer together, this happens, that the proton, surrounded by the electron cloud of one atom, as it comes close and interacts with the protons and electrons cloud of the other, there are two repulsions and two attractions. And I have it on the right here in this little better diagram than I have. But as they come close together, the dominant force is going to be the attractions, the electron clouds to the protons of each nucleus. So as the atom gets closer and closer, finally you'll get to a point, we'll call it right there, where the repulsions equals the attractions. That becomes the bond length. We'll put R sub 0, bond length. And for hydrogen, this bond length is 74 picometers. This is from the positive point to the positive point. Half of that becomes the covalent radius of the atom, and you'll see that is about 37 picometers. Remember, a picometer is 10 to the minus 12 meters. That's small. So in fact, hydrogen is the smallest atom of all the elements in the periodic chart. So hydrogen has a bond length, and it's associated with the repulsions and the attractions being balanced as the two atoms come together. The second one is more interesting, I think, and this is, as the atoms come together, energy is given off. and it reaches a low point where if you push the atoms any closer together, you're squeezing out the electrons between them, and it very rapidly rises. This low point is the point right here in energy. This is negative here. Minus 436 kilojoules. It's about right. This is the energy given off when this bond forms, reaches this radius or bond length of 74 picometers. Let's talk about this energy, potential energy here. It's given by an equation adapted slightly from a famous equation called Coulomb's law. Famous Frenchman, engineer, member of a very wealthy family who discovered this electrostatic law, and the fundamental unit of charge, the Coulomb, is named after him. He also survived the French Revolution. His friend Lavoisier was beheaded, but he made it out. So Coulomb's law is adapted so you have a constant, and you have the charge, the positive and negative charges, Q1, Q2, and inversely related to the distance between these charges. Well, how does it come out to be energy, joules or kilojoules? I will just derive that very briefly here so we can take a look at this. Dimension analysis is very important in chemistry. The constant K has the units of newtons times, newtons times coulombs, no, meter squared. Yeah, I'll get this right. I'm just looking ahead. Meter squared over coulomb squared. And it's going to be multiplied times Q as coulomb squared over this distance, meters. And why I paused, I wanted to make sure I had this right. Because see, the coulombs have to cancel out, and you get meters alone up here. And you get a unit newtons times meters, and the newtons is the force times the distance, that's work, that's energy, that's joules. So this unit is in joules. So what we have here is an equation where one hydrogen atom combines with another hydrogen atom, monatomic, that means single atoms, and they become a diatomic hydrogen. In so doing, they give off 436 kilojoules. Another way of looking at this, and this is the way we could identify this energy concept easier, is to take regular hydrogen gas, easy to make, and dissociate it. Use 436 kilojoules, and we'd end up with single hydrogen atoms, or monatomic. These hydrogen atoms do not exist except at high temperatures, or at they've stabilized hydrogen atoms near absolute zero also. But hydrogen in normal temperature exists as diatomic. Now we're going to use this concept, length and bond energy, for every bond there is, and we're going to use it throughout the rest of the course.